Chemical Bonding, Part 2. Have out your reference tables and turn to the periodic table as we continue our discussion of covalent bonding. When we look at this diagram, we're going to consider the Lewis structures of three compounds: water, ammonia, and methane. If you look at the top example, you see that water is made up of oxygen with 6 valence electrons and 2 hydrogens, each with 1 valence electron. In ammonia, we have nitrogen with 5 valence electrons and hydrogen with 1 valence electron each. Now look at methane at the bottom. Methane is made up of 1 carbon atom that has 4 valence electrons and then 4 hydrogen atoms, each with 1 valence electron. Take a look at the hydrogen atoms. All hydrogen atoms have 1 valence electron. When they combine with the oxygen, nitrogen, and carbon, you're going to wind up with a stable octet around the oxygen, the nitrogen, and the carbon. And then the hydrogens are each going to have 2 valence electrons, which is going to give them a stable electron configuration as they look like the helium atom with a completely filled first energy level.
Covalent bonding occurs when neither atom has sufficient strength to completely remove the other atom's electrons. The atoms share electrons, and both atoms achieve a stable outer energy level. A hydrogen atom with 1 valence electron needs 1 additional electron to complete the first energy level. An oxygen atom has 6 valence electrons and needs 2 additional electrons to complete the second energy level. As the oxygen and hydrogen atoms collide, covalent bonding is accomplished by the sharing of electrons. By sharing an electron pair with the oxygen, the hydrogen completes the noble gas configuration of helium. By sharing with the hydrogen atom, the oxygen atom now has 7 electrons in its energy level, still 1 short of the stable octet condition. A stable octet for oxygen can be completed by sharing an electron with another hydrogen atom.
Let's look at the properties of covalent substances. They form molecules. They're soft and brittle as solids. They're insoluble in water. They have low boiling points. They have high vapor pressures. They're poor conductors of heat and electricity, and they are slow reacting. Now let's look at the 2 different types of covalent bonds. The first type is called a nonpolar covalent bond. In a nonpolar covalent bond, the electrons are shared equally. In order for the electrons to be shared equally, each atom involved in the bond must have the same electronegativity. The diatomic elements all form nonpolar covalent bonds. In the diatomic elements, the electronegativity difference is 0. Notice that oxygen is sharing 2 pairs of electrons. The oxygen molecule is made up of a double covalent bond. Nitrogen shares 3 pairs of electrons, and the nitrogen molecule is made up of a triple covalent bond. All of the other diatomic elements are all single bonds. The diagram of the hydrogen molecule and the chlorine molecule is also shown in this diagram. Hydrogen is a single bond, nitrogen triple, oxygen double, fluorine, chlorine, bromine, and iodine all have single covalent bonds. Now let's consider the polar covalent bond. In polar covalent bonding, the electrons are shared unequally. One of the atoms involved in the bond has a greater attraction for electrons than the other atom. This means that the bonding electrons are closer to the atom with the larger electronegativity. If you look up the electronegativities between the 2 atoms and it is greater than 0, but less than 1.7, it is a polar covalent bond. In the Lewis structure of water, we see the sharing of electrons between hydrogen and oxygen. Since oxygen has a higher electronegativity, the electrons will be closer to it than to the hydrogen. The electrons are not evenly distributed. In this methane molecule, the electrons are not evenly shared. In the methane molecule, carbon has a higher electronegativity, and the electrons will be closer to it than to the hydrogen. Let's consider the formation of hydrogen chloride. The electrons are going closer to the chlorine atom because chlorine has a higher electronegativity. Since the bonding electrons carry a negative charge, the closer they get to the chlorine atom, the more negative the chlorine is going to become. And the farther they get from the hydrogen atom, the more positive the hydrogen becomes. A partial positive charge is created on the hydrogen atom, and a partial negative charge is created on the chlorine atom. It is not a complete charge, it is a partial charge. Molecules in which there is a partial positive and partial negative end are called dipoles. Well, now we have to consider the shapes of molecules. The shape of a molecule can determine many of its physical and chemical properties. You should be familiar with the 4 most common types: linear, bent, pyramidal, and tetrahedral. Let's consider Figure 1. Figure 1 is made up of hydrogen and chlorine. The chlorine is the green, the hydrogen is the white. Now, chlorine has a higher electronegativity, and so the electrons are going to be closer to it. The shape of this molecule is linear. All 2-atomed molecules are always going to be linear. Now, because of the difference in electronegativity, this molecule not only has a polar covalent bond, it is a polar molecule. A partial negative charge exists on the chlorine atom, and a partial positive charge exists on the hydrogen atom. Now let's skip over to number 3. Figure 3 represents a molecule of hydrogen, H2. The bond between 2 hydrogen atoms is going to be nonpolar covalent. This molecule is linear and it's symmetrical. As such, that is a nonpolar molecule. As we discussed in our unit on solubility, we would know then that hydrogen chloride, polar, would not be soluble in hydrogen, nonpolar. Likes dissolve likes. Now look at number 2. Number 2 is the carbon dioxide molecule. Oxygen in red, carbon in black. Now oxygen has a very high electronegativity. Oxygen has the second largest electronegativity on the periodic table. That means that the electrons are going to be closer to each oxygen atom. That means that the chemical bond between the carbon and the oxygen is going to be a polar covalent bond. Notice that it's a double covalent bond that holds the oxygen atom to the carbon atom in carbon dioxide. Now, the bonding is polar covalent, but carbon dioxide is a linear, symmetrical molecule. Since it's symmetrical, it is a nonpolar molecule. So even though the bonding is polar covalent, the molecule is nonpolar. That means that carbon dioxide could dissolve in hydrogen because they're both nonpolar. Let's look at model number 4. Model number 4 represents the water molecule. Oxygen in red, the 2 hydrogens are in black. Again, oxygen has the higher electronegativity, so the chemical bonding between the oxygen and the hydrogen is going to be polar covalent, with a partial negative charge on the oxygen, partial positive on the hydrogen. The shape of the water molecule is bent. Because water is bent, it is not symmetrical. Bent molecules are never symmetrical, which means that the water molecule is going to be a polar molecule. Water is an extremely polar solvent. That's what makes it so important when it dissolves salts and other polar substances. Continuing to number 5. Number 5 represents the ammonia molecule, nitrogen with 3 hydrogens around it. Nitrogen has a higher electronegativity than hydrogen, meaning that the electrons are going to be closer to it, and ammonia is a pyramidal molecule. Pyramidals are never symmetrical. That means ammonia is a polar molecule. The nitrogen has the partial negative charge and each hydrogen has a partial positive charge. This also means that ammonia would definitely dissolve in water. In number 6, we're looking at carbon tetrachloride. Carbon with 4 chlorines around it. Chlorine has a much higher electronegativity than the carbon atom. That means each chlorine atom is going to pull the electrons closer to it. Chlorine has a partial negative charge and the carbon has a partial positive charge. Now, this is a tetrahedral molecule. Carbon with 4 atoms around it are tetrahedrals. Now, since all 4 of the atoms surrounding the carbon are the same, they're identical, that means that carbon tetrachloride is a symmetrical molecule. Since it's a symmetrical molecule, carbon tetrachloride is non-polar. Go over now to number 7. Number 7 represents carbon bonded to 2 chlorines and 2 smaller hydrogens. Well, you can look at this and see this is not a symmetrical molecule. All 4 atoms around the carbon are not the same. That means this molecule is not symmetrical, it's tetrahedral, and because it's not symmetrical, it is a polar molecule. In our last example, number 8, we have, again, carbon surrounded by 4 hydrogens. Carbon, in this case, is red, and the 4 hydrogens are each blue. Again, this is a tetrahedral, but as such, it is symmetrical. The 4 hydrogens around the carbon atom are identical with identical electronegativities, meaning it's a symmetrical molecule. Symmetrical molecules are never polar. Let's now consider London dispersion forces. London dispersion forces of attraction are present in all molecules. They hold molecules together based on the creation of momentary positive and negative charges caused by the random movement of electrons around an atom. That means that the more electrons in an atom or molecule, the stronger the London dispersion forces are. When considering the halogens, find the halogens on your periodic table: fluorine, chlorine, bromine, and iodine. Since iodine is the largest molecule, I2 is the largest molecule, its London dispersion forces are the greatest, and that is why iodine is a solid. Bromine, Br2, is the next largest molecule with slightly weaker London dispersion forces, but they're strong enough that molecular bromine exists as a liquid. Chlorine and fluorine are small molecules with even weaker London dispersion forces. They are both gases. London dispersion forces explains the generalization that small molecules tend to be gases while larger molecules tend to be solids. Dipole-dipole attraction is the attraction between polar molecules. It is the attraction of the positive end of one molecule with the negative end of an adjacent molecule. When the polar molecules line up with positive ends directed towards negative ends, the entire sample is held together so the sample does not act like a bunch of individual molecules. Our last type of London dispersion forces is hydrogen bonding. Hydrogen bonding is a type of dipole-dipole attraction. It only exists between hydrogen fluoride, water, and ammonia molecules. Because hydrogen bonding is the strongest of all intermolecular forces of attraction, we need to be thankful for how strong it is in the water molecule, because it is responsible for water being a liquid at room temperature.